So in this video, we're going to identify the common features of the seafloor. We'll explain the difference between abyssal hills, seamounts, and mid-ocean ridges. And we'll also talk about how you can tell if a seamount was once an island. So in the last video, we talked about advances in measuring ocean depth over the last 150 years or so. But nowhere else is this more evident than in the mid-ocean ridge of the Atlantic, or the Mid-Atlantic Ridge. So beginning in the last century, you can see how this feature started to come into focus. This is the spine in the middle of the Atlantic Ocean here, and you can see that by the 60s, it was pretty easy to tell that this feature existed, but over the last 50 years or so, the abundance of these faults and other smaller features come into focus more. Remember that these high-resolution maps are mostly generated by satellites. So this is the view we have today, and so we'll go through some of the really prominent features. So this is what's called a false color image, and that means that the colors here are assigned digitally to highlight the contrast in different features. So you can see in the oceans, depth goes from this deep blue color, purple in some areas, to this green color that's just below the sea surface. Then once you're on land, you go from this deep green color all the way up to this brown color at the highest mountains. For the meantime, just stare at the ocean for a second here, if you can focus on the Pacific at least, and look at what features start to pop out. Well, one of the first features I think that has probably caught your eye is this mid-ocean ridge system, which runs across the entire globe. This is the single largest continuous feature of Earth's surface. It's essentially a 65,000 kilometer seam that runs from the Arctic down through the Atlantic, across the Southern Ocean, through the Indian Ocean, and here it sort of splits. You can see that there's one leg that goes up here into the Red Sea, and there's another leg that keeps going through the Southern Ocean into the Pacific and up into the North Pacific here. So at these mid-ocean ridges, you can see topography begins to rise from these really deep features in these abyssal plains up to the ridge axis here, which are only around 3,000 meters below the surface or less. You'll notice how many of these sort of horizontal fault features you can see in these mid-ocean ridges, especially in the Atlantic. These are at a right angle to the main direction of the ridge. So it's important to keep in mind that the height of these mid-ocean ridges is pretty significant, and it's hard to tell sometimes in a false color image, like in the previous slide. For comparison, here's a cross-section across the continental US. California over here, Sierra Nevadas here, the Rocky Mountains, then the Appalachian Mountains, and then the east coast of the US. So you can see that the Appalachian Mountains are barely 5,000 feet tall, well, only around 1,000 meters tall. And then the highest points of the Rocky Mountains or the Sierras are closer to around 3,000 meters or 10,000 feet above sea level. So now if you look at a similar cross-section for the Atlantic Ocean, you can see that from this lowest point here in these abyssal plains, the mid-ocean ridge is around 10,000 feet above those. So it's basically the height of the Rocky Mountains in height. So this is a continuous mountain range that runs through the oceans that you can't see from the surface. So you can tell from this cross-section that mid-ocean ridges are really the dominant feature of ocean bathymetry. There's a couple more we can also go through as well. One that's already been mentioned so far are these abyssal plains, which are these flat, featureless expanses of sediment-covered ocean floor. So in the abyssal plains, the actual rocky parts of the seafloor are covered by these really fine-grained sediments that blow in from the continents through dust or from rivers. These sediments can also be generated from organisms that live in the water column and that they make shells, for instance, that then coat the seafloor. But in certain areas, you'll also find these manganese nodules, which are shown here zoomed out and then here close up. These are about a cannonball in size, and they're primarily made of this metal called manganese, but they're also enriched in economically really important metals like cobalt, nickel, and rare earth elements, which are used in a number of different high-tech applications. For instance, cobalt is used in the batteries in Teslas and in smartphones, and so it's really key to a lot of the electronics that we rely on today. Currently, a number of these elements are mined in places that are kind of problematic. So for instance, most of the world's cobalt comes from the Democratic Republic of Congo, and the mining conditions there are really dangerous. There's a lot of child labor, and that money fuels regional conflict. So there's been some interest in trying to find alternative sources of this metal in these manganese nodules in the ocean. The catch, though, is that this mining would be really destructive to this ecosystem, which typically experiences very little change. This is a very stagnant part, and the organisms that live here are really reliant on that fact. So currently there's a moratorium on deep sea mining, but this is something that may open up over the next couple of years. So it's something to pay attention to. So here's the distribution of abyssal plains throughout the ocean. You can see that they're usually interrupted by mid-ocean ridges, for instance, in the Atlantic here, or parts of the Pacific or the Indian Ocean. They're really the sort of baseline state of the seafloor. And so they mostly occur where other things like mid-ocean ridges or seamounts don't occur. Okay, next let's talk about abyssal hills. So these are relatively small. They're a bit hard to see unless you have a high resolution version of this map. But you can see the sections of the mid-ocean ridge here are dotted by these small changes in bathymetry here. These are the abyssal hills. Each one is maybe a few hundred meters tall, usually less than 1,000 meters tall. And they're sections of either folded crust or extinct volcanoes. And they're mostly found, like I said, bordering the mid-ocean ridges here. You can see more, for instance, in the South Atlantic Ocean here. This is an example of abyssal hills in the Southeast Indian Ridge and the Mid-Atlantic Ridge. This dip here is from the center of the mid-ocean ridge. This is often called the axial valley. And then the abyssal hills, in contrast, are on the sides of the axial valley. So you can see they often occur in these sort of parallel lines, parallel to the ridge. So you can see some here, there's some here, there's some here. You can see the same thing in this Atlantic Ridge. There's a street, there's abyssal hills here, section of hills here, and here. So abyssal hills are these relatively small changes in ocean depth that you find especially close to mid-ocean ridges. In contrast, there's larger features such as seamounts and guyot. These are volcanoes that occur off of the ocean ridges, but they don't rise above the sea surface. So there's a few examples here. There's several along the Hawaiian Islands, including many of this emperor chain of seamounts, a couple off the main axis of Hawaii. There's a number of them in the rest of the tropical Pacific. These all don't break above the surface of the ocean. So a seamount is just a volcano that has never been at the seafloor. Usually they have this sort of classic volcano-like shape where they're sort of cone-like. But in contrast, guyot is a similar mountain, but it has a really flat top here. So you might think for a second why it has this flat top. These are both generated by the same process, which are volcanic eruptions on the seafloor. But this guyot here has to be weathered very differently than the seamount. The only way you can really think about that happening is at the surface. Once the seamount becomes tall enough and its head pokes above the water, then officially it's an island. But also, once this happens, it's subject to a lot more intense rain, sometimes snow, wind, and all these forces will eventually weather the top of this mountain and flatten it out. Once the main mountains on this island are gone, then wave action will do the rest of the job to really flatten this straight out. You can see this in a number of atolls across the Pacific. They're generally flat at the surface. And the key thing here is that the forces of erosion are much stronger above seawater than they typically are below seawater. So that's evidence that these guyot here used to be islands that have then sunk back down to the ocean depths. Whereas a seamount never became an island. It never broke the sea surface. Now the reason these both end up sinking over time is because their heat source is lost. So when these are active, they're sustained by magma that's just underneath their surface. And this heats up the whole seamount as a whole. But when that heat source cools, and the rest of the seamount or island cools, then the rock basically contracts and becomes smaller. As it becomes smaller, it becomes more dense, and through isostatic equilibrium, it sinks back into the crust. So this atoll that was once basically level with the sea surface is now 1,000 meters or 2,000 meters below the sea surface. All right, moving on. So another really prominent feature of the ocean are these island arcs. These are chains of islands that pop up above the sea surface. Great example of the Marianas Islands here. The Philippines are an example of an island arc, as are the islands near Tonga, Fiji, all the way down to New Zealand. And the islands of Indonesia as well are sort of these classic island arcs. Usually they have this bent structure here. They're not a perfect line. They usually have some kind of curvature. Well, the Aleutians here are another perfect example of this. So these are going to be really crucial when we discuss plate tectonics later on. Now, these island arcs usually enclose what's called a marginal basin, which are these distinct sections of the seafloor that are cut off from the main ocean. So you can see some in the Bering Sea here. You can see the Sea of Japan or the East Sea here. South China Sea is another great example of this. The Black Sea is a good example of this. These are all relatively deep features, 1,000 meters depth or more. But because they're surrounded by these island chains, they're cut off from the main ocean. They don't necessarily exchange water as fast. Because they don't exchange water as fast, they can have their own unique properties compared to the open ocean at large. But the closing off of these seas is really the result of the formation of these island chains. You can see these links emerging here. Without the islands in the Caribbean, for instance, the Caribbean would still be connected to the Atlantic. Oh, and one more thing is that margin just means the side or the edge. So these occur at the edges of continents. Another important thing to note is that these island arcs are almost always found alongside trenches. So you can see in the Aleutians here, you have this whole island arc here, but then right in front of that, you have this section of extra deep seafloor here. The deepest part of the ocean is the Marianas Trench. You can see this trench sort of curling around the Marianas Island arc. And this continues on through Japan, through the Kuril Islands. There's trenches on the other side of the Pacific Ocean as well. This is the Peru Trench that covers most of South America. And there's a trench in front of Puerto Rico as well. So these trenches almost always co-occur with different island arcs. Okay, and so the last important feature that we talked about already is, so the last feature to discuss are these continental shelves. We've already talked about how these are formed because accumulation of continental sediment pushes this part of the crust below the sea surface through isostatic equilibrium. This extra weight pushes the continents down further into the asthenosphere and submerges this section of the continent below sea level. So there's a great example of this sort of between Australia and Papua New Guinea, but also between Borneo and Southeast Asia. There's large continental shelves off the east coast of the US as well. And these will change a lot over geologic time. But remember, these are still continental crusts, and so they're still much more buoyant than the oceanic crust. And that's the reason why they aren't as deep as the main ocean. This is also what differentiates them from marginal seas, which still have oceanic crust at the bottom. So you can see, for instance, the East China Sea is really a continental shelf. It's not very deep. It's all on the same continental crust, whereas the South China Sea is a marginal basin because it still has oceanic crust that's relatively deep. Okay, so in this video, we've listed through some of the really common features of the sea floor. These include the mid-ocean ridges, the abyssal plains, seamounts, guyot, abyssal hills, island arcs, trenches, marginal basins, and continental shelves. Remember that seamounts are volcanoes that never reach the ocean surface, but guyot are former islands that have shrunk back to the ocean depths. And it's this erosion at sea level that leaves this characteristic flat top that defines what a guyot is compared to a seamount. Both seamounts and guyot are also much bigger than abyssal hills, which are these small changes in topography at the edges of mid-ocean ridges. Remember that abyssal hills also come in these parallel lines away from the mid-Atlantic ridge. And actually, these abyssal hills are one signature of seafloor spreading, which is what we'll talk about in the next video.